Welcome George Labahn from Waterloo. He'll speak on dynamical systems and scaling invariants.
Thank you, Alexei, for inviting me. In fact, the first talk I submitted to Alexei was on integration of convolution function. But then I didn't see differential or difference in any of the slides, and so I thought I'd change it. And in fact, what I decided to do is talk about this topic, which is very similar to what I talked about yesterday. In this case, again, as in yesterday's work with Evelyn Lebert from Invariants in France. And so what happens is, in fact, this is kind of the first part of two talks. Yesterday's was the second part, I thought. It's the easy part of the two, but nonetheless, the disadvantage is I use a lot of slides, which is easier for me to do, but will require a little repetition for yourselves. But I will try and at least show you where there's differences in the. So this is a report on the paper by Evelyn and myself that appeared in Foundations of Computational Mathematics last year. And there's other relevant publications, used by Evelyn and myself, both the paper I talked about yesterday and another paper that appeared in ISAC a couple of years. And whoops. So let me give some motivation first. And so here's an example of an equation, dynamical equation, dynamical system, predator-prey model that comes from a book from mathematical biology, a Murray author. And it's two derivatives, two variables, and about 6 parameters. And if you look at that equation, it turns out that these things are sort of invariant under a 3-parameter group action, where the parameters are mu, and v, if you like. And so if you sort of basically what I'm saying is if you take these sort of replace t by this, r by this, etc., you get exactly the same set of equations. It's totally invariant. And what happens is you can take advantage of the fact that this invariance to get a second system. And what happens is you can you get an equation, again 2 equations, but this is easier. You have considerably less parameters. And I guess this is when people are modeling dynamical systems, and Francois can maybe add something to there sometime after the talk, that people sort of add parameters that they think are correct, but at the end it's quite often too many parameters. And there's a process that they follow to sort of reduce this number of parameters. Okay? And the procedure I'll describe actually does that for us. Okay. And note that sort of at some level there's sort of 9 things floating around, and now we've reduced it by 3. And that's going to show up for some reason. Okay. And so the second equation, here again, it's 2 equations. 2 unknowns, derivatives in t, and here we have sort of things invariant under this time a 1-parameter group fashion. In this case, we replace the system by sort of these 3 equations, which already seems a little bit unusual. 2 equations instead of 3. But in fact, the initial system is really sort of a hidden equation somewhere there when you take derivatives. And what happens is we sort of find that these 2 equations, they've reduced it to something where they take advantage of the fact that they're written in terms of things that are invariant under a transformation. Namely, this initial system was sort of, you can replace the variable by this, and get a new system. And what we do is we find things invariant and sort of write them in things that are now invariant under these transformations. And I'll sort of show you where. And incidentally, this is not really a difficult equation. Here you can see, in fact, it's basically a quadrature. It's basically an exponential of an integral of something which is determined that you saw in the first equation. So it's like 2 equations, a dynamical system of 2 equations. So what does this talk about? It's about scaling symmetries, basically sort of a group action on some variables. Here are 5 variables. And as it happened, resulted in happening the other day, yesterday, So the action is going to be just take the individual variables and rescale them. And you can write we're going to have sort of a type of scaling where the scaling can be written in terms of generators of the particular group. So these will be non-zero entries. And so this time around we don't have a finite group, we have an infinite group, 3 parameters. We're going to determine important instruction for the group action, namely rational invariance, and rewrite rules exactly as done yesterday. And actually, I expect to be done next by your talk. You mentioned the same thing. So by Rina and Kogan in the next talk. We're going to again use linear algebra to solve the scaling symmetry problems. And again, it's going to be simple, using everyday tools. And the solution just kind of falls out, makes things nice and easy. As a matter of fact, it's so easy you don't even bother listening to an algorithm. People can just do it without. And it gives a reduction of dynamical system polynomial systems given a scaling. It makes things easier. In this case, it makes things easier by actually reducing the number of variables that are floating around. And so the outline again will be we'll sort of formalize these scaling symmetries. We'll give sort of an exponent type form for these, exactly as seen yesterday. We'll talk about integer linear algebra, sort of exactly as yesterday with the variation. And then we'll show rational invariance and rewrite rules again from this integer linear algebra. And then I'll show you how we use this to reduce dynamical systems. Previous work done in this regard is Francois Lemaire and his student Eggerpure. Give a talk, not bad, eh? Give a talk on this in ISAC 2010. Nevelin did some work on Alexandra Sedligovich in 2006, and Alexandra also did something separately in 2007. Alexandra is also a researcher at Lille. And scaling symmetries themselves are used in reducing dynamical systems, reducing polynomial systems. So now you'll get polynomial equations again with a certain number of unknowns. You reduce them to having fewer unknowns and easier to solve. And dimensional analysis. And in all these cases, it's just not a matter of reducing, but it's a matter of reducing and then solving and then returning. So it's, just reducing something isn't good enough. You have to reduce and somehow get back a complete set of solutions after you've solved a reduced system. And it's possible to do that too. Okay, and so here we're going to have a little bit of repetition from yesterday. And we're going to describe exponent matrices and matrix notation. And so here again, here in the scaling I described in the earlier slide, we rescale according to some powers, some parameters with various powers. From these, we take the exponents of each power, we arrange them into a matrix where there is a sort of a column for each variable, and the exponents themselves, sort of basically a description of the free parameters in the available in the group, and so they'll provide that number of rows. And so we get, in this case, a 2x5 matrix. So pretty straightforward. And we use some sort of exponent notation where we take the 2 parameters and raise it to exponents, and this will give us the exponents for a certain number of columns, and the exponents are done on the parameters themselves, group generated. Okay, and again, the scaling symmetry in this case is described as something which is basically a pointwise multiplication of sort of a set of parameters from the free parameters from the group with certain exponents, and then pointwise multiplied individual variables. That's group action, and it has properties like an exponent. And then we talk about integer linear algebra. We're going to use the exact same tools, Hermite normal form. We're going to talk about a unimodular multiplier and a normalized unimodular multiplier. In this case, it's going to be quite a bit simpler than what was done yesterday. So again, we're going to do exactly the same structure as yesterday. Namely, you have a matrix. This is our exponent matrix. There's no order matrix anymore in this case. We want to be able to reduce it to a Hermite normal form, and remind people the Hermite normal form is it's a triangular matrix. The diagonals are positive, and everything below the diagonal is less than the diagonal on the other in the same row, and that zeros come at the end. This is the column reduced form. And then there's also sort of a set of column operations, which require integer operations only. You're not allowed to divide or form fractions. And this is the sort of what we call the unimodular multiplier. And so original matrix, a set of column operations, gives you this reduced system. And we're going to apply it to the exponents. And now here in this case, so we have sort of a right side which basically describes the kernel of the exponent. This is in blue, and in the red it provides the image. And again, we have no problems with the fact that there's an exponent matrix around. And so this will be strictly sort of operations applied to, if you think about it, the exponents themselves on the scale. Okay? And again, unimodular means that this process is always invertible, which just always happens with column operations. And as before, I mentioned before, it's very easy to sort of take these columns, do any sort of manipulations without changing, keeping this as unimodular, keeping these zeros here. Even if we take the columns from the last three, you sort of like double this column and add it to the first column. It won't change anything. It'll still be a reversible process, and it won't change the right-hand side. So it's not unique. We can make it unique, in this case, by sort of taking the bottom part and making it into Hermite number form. So basically, making it triangular on the bottom, or at least as far as we can on the bottom. It might not be the bottom rows, it might have to be a little bit higher. And from that point on, then everything else must be less than these diagonals. And the diagonals, the Hermite number form part of it is only on the kernel part. That's kind of important in this case. Okay. So this is a norm, it's called a normal unimodular. So scaling invariants. As before, a function is invariant, and the scaling, if when you basically take the variables, you have an expression in variables z1 through to zn, you rescale the variables, you plug them back in, and nothing changes. Okay? Which is obvious notion of invariance. And in this case, we have the fact that to be invariant, basically for a monomial here, written as z1 through zn with the various components there, we can distribute the v through from one of the properties, and that's the same thing as saying basically the fact that now the exponent is going to be in the kernel of the matrix A, and the Vn, the part in blue from before, basically provides the basis of an integer, of the modulo of integers for the kernel, and that's very convenient for us, very important for us. So the things that are invariant, the little terms, individual terms which are invariant, really require the exponents themselves to be in the kernel. And also for rational invariance, it's not so obvious, but in fact, what happens with rational expressions, that they reduce to a system where all the exponents are in the kernel themselves. So not just sort of one term, but if you have rational expressions, you can sort of show that if you look at the support of the numerator and denominator, that they somehow have to be represented by exponents. You might have to pull out a sort of common exponent, but if you pull out the same common exponent top and bottom, they'll cancel. And what you're left with is always exponents in the kernel. And that's also central. And in this case here, what we have is, so again we have our matrix of exponents. We have R variables, sort of R parameters in the group, and variables. And the kernel is described by n minus R. Because, well, we sort of start off assuming A is full rank. You can deal with it if it's not full rank, but we'll assume it's full rank R, so H is the square matrix. That leaves n minus R components in the kernel, always described by this part of the unimodular multiplier, which is the Hermit normal form conveniently for us. Here's an inverse of H, or of V. And it turns out that if you want to find the invariants, all invariants are actually determined by the original variables, the raised to the exponents described by the kernel. But NHS is any kernel in this case, but normalized ones work best for us. Okay, so determining the invariance in this case, the n minus r invariance, is trivial once you've done this operation on the exponent. Furthermore, if you sort of want to sort of rewrite any invariant rational function, then it's sort of this basically rewrite rule, which is basically a substitution rewrite rule. You simply take the invariance to the powers now described by the bottom part of the inverse, and you can compute the v and the w simultaneously, so it's not a computational issue. And you'll get a rewrite rule also. And why does this work? In this case, it's easier than what was done, for example, yesterday. So in fact, you have this identity because v and w are inverses of each other. So you have this identity here. And it turns out that the upper part, the lower part, the upper part actually, anything that's in the kernel of v is also actually in the kernel of w. So you can rewrite any exponent from this because of the identity. You can distribute them because one of the properties of exponent. And then, in fact, this disappears because this is 0, and so this is part of just 1 by itself. Okay? And so that means that any exponent is really written like this, which can be summarized this, and this is just the invariant. And so you have the invariant raised to this power of this exponent, and so anything like this can be replaced by this. And any rational function must look like this, where v comes from the kernel. And so consequently you get this property right here. So let's give some examples of this. Here, the running example I've been using, the v and the w that I've been using. So invariants are here, for example, the invariants, there's 3 of them, one per column. Take the original 5 variables. Use exponents that come from the last 3 columns, and you'll get these monomials. And these are the invariants. And they generate all invariants. Any rational invariant is basically a combination of these. And a rewrite rule is then just sort of take your original variables, and you can rewrite them by taking your invariants, but now using the elements in blue in the inverse matrix as the exponents. And here you'll get, these are your rewrite. This is your rewrite rule. Z goes to this. And for example, this is a rational invariant under sort of this action. And if you want to see what happens there, you simply replace the z's by the y's, and you get a much simpler expression. So, this is the process. I want to show, if I want to reduce dynamical systems, I want to do reducing parameters, reducing systems, and I'll just describe this a little bit. So, for example, the predator-prey model. In this case, you have a scaling matrix that looks like this. Unimodular multipliers look like this. Here, this describes the kernel. This describes the inverse. And so these will be the exponents of the invariants. These will be the exponents of the rewrite rule. And note that here, these are all zeros. And so what's going to happen? The exponents are all 0, which basically says you're going to rewrite some variables by replacing them by 1, which of course is very easy. So I'll show you what happens there. So if you take your original system here, here are the invariants. They come from the exponents from before, from the v. These are the exponents, and if you want to check, just take a column and just sort of find the corresponding variable here. And your rewrite rule is, let's say you basically have a rewrite rule that takes the first 3 parameters, because we've ordered it a certain way, and basically rewrites them as 1, and everything else is rewritten in this new set of parameters, a new set of variables. And so you take this system and you can rewrite it just by, for example, if you see an R, replace it by 1, a little h, replace it by 1, big K, replace it by 1, and then you get this system. And you have a system with less parameters, much simpler. Okay. Now, so the dynamical systems, what happens is we like to write our dynamical systems in this way. Is z prime equals to z componentwise multiplication by a function which is then invariant under scaling. And in fact, what I'm not including in this talk is the fact that you can actually sort of, we're going to sort of say that we have a matrix A, the scaling, but in fact you can find this matrix A. So I will just assume it's given, but in fact there is a procedure, again involving actually a Hermite normal form computation, interestingly enough, a different one though. But we'll find a scaling that will work for us. And as long as you have a non-trivial scaling, you can sort of determine the information. You can define the kernel, the image, that's inverse. And then what happens is you can rewrite this system here by a smaller system, a system in Y, that's a system in invariance, and where everything is sort of determined by either the inverse matrix or the exponent matrix or the null space matrix. And so the equation in invariance and in something sort of a dynamical system only involving something auxiliary variables. And these auxiliary variables are really, as I say, it's really an exponential of an integral of these expressions. So that doesn't involve the x. So once you solve this, you can get you can solve for the y as exponential of an integral of some expression. So de facto it works. And if you take these two systems, a dynamical system and invariance, and something with the auxiliary variables, in fact, what happens is you can reconstruct a solution to the original system. So you can reduce the system, and you can build back a solution from a reduced system. I'll give you another simple example here. And this is an example we used where the system that resulted from solving this dynamical system here was considerably easier than this type of solution that came out of Maple, for example. We determined that there was a scaling in this dynamical system of the fact you could sort of multiply x by z1 by lambda and z2 by minus lambda. T was not part of the scaling. And then, so this sort of this was invariant under this. And then here's sort of the null space image, again, inverse. And so the invariant is the exponents here. Auxiliary variable turns out to be what was left over here. And you could reduce these two systems to these two systems. And again, you could solve this one easy enough. This one was a quadrature formula, and basically the solutions were, once you solve y, you get a solution for x, and this gave you a solution both for z and z1 and z2. Okay, so it turns out to be quite effective. The methods sort of describe extensive systems with symmetry on T. I sort of didn't spend so much time on that. You have to do a few little different things. We combine scaling symmetries with finite diagonal actions. And in fact, I should mention the following. So what we did also when we did this is we went through this Murray book. We took all the examples of the Murray book. And it turns out that this Murray book has all these equations from mathematical biology. And they use sort of ad hoc methods to get rid of parameters. We applied our software, simple software to all these to reduce the parameters. In almost every equation there was sort of a significant reduction of parameters. And so reducing for parameters was definitely something that was very effective in this method. And there are cases where sometimes you have two things happening. You have parameters in the dynamical systems. You also have sort of things like finite permutations working on. So basically, today's talk and yesterday's talk together. And so all of a sudden you have to sort of combine them. And again, you can do it this way, where you sort of basically work with exponents and an order, and you can, after diagonalizing first, and then you can do a Hermite computation. You can find both the reduced set of scaling invariants and a way to reduce it according to the finite abelian order. So that turns out to be quite nice. And that's a fairly common scenario that I can see. Again, these are also situations where you're taking advantage of the fact that models are built and they sort of have this, from real life, and they have this structure which you sort of don't take advantage of. People are seem happy enough to write equations, but it comes from a physical system, and the physical system has structure. And then it's our job to sort of solve these systems taking advantage of this structure. And finally, I should mention, I think I mentioned this a little bit, you can find, in fact, if you start off with a system, you can actually sort of, it's not just sort of, somebody has to determine the scaling matrix, you can actually find that itself, and then apply, from the equations themselves, and from that you can build a scaling matrix and invariants and reduce everything. And that's my talk.
Thank you. Questions?
Well, more a comment, actually. I like this very much, but
that's a good comment. You can stop there.
I think it could be extended a little bit. And actually, I also am a little bit upset about what calculus is taught to engineers, because mathematicians will use all dimensionless variables, basically. But the engineers will have dimensional variables, and we'll try to calculate something like the exponential of a second.
Yeah.
So dimensionless plus a second squared plus a second cubed is utter nonsense.
Yeah, that's right.
So the idea of a dimensionless variable is very critical. On the other hand, when you write down equations in physical systems, it's better to use dimension variables, because that allows you to check your equations are balanced.
That's right. Yeah, that's exactly.
So the ideal way is to use dimension variables to write your problem down, and then you make the variables dimensionless, and then you look for parameters that are also combinations of parameters that are also dimensionless. And I think it's almost the same as you go, although it looks like your parameters would always have a...
No, I expect, but it's exactly what it is. So it's like this dimensional analysis that you sort of reduce you combine the parameters together until they're dimensionless, and then you get a reduced system with fewer parameters. You solve that, but the key thing is you can solve it and you can work backwards, because when engineers want to give their parameters in there, some level it has meaning for them. They don't look at the ratio of this to this so much.
Well, most of the things that people mention as parameters in physical systems are of that nature, right? They will have dimensions, but they really relate to it.
Yeah. But at the end, they do want to mention the parameters back, the original ones they use, just to get it, because that's what they sort of feel.
It's better to compute with the dimensionals.
Obviously, exactly.
Either symbolically or numerically.
Exactly, because it's too many.
And then translate the answer back.
Yeah, for sure, and that's what this describes. Because not only does it reduce, but it's sort of a situation where reduce, and you do your work, and then it goes back.
And it's also messed up in biological.
Yeah, that's what we found in that book.
A lot.
It's quite something.
It's a mess.
You mentioned early on that it's very useful to normalize the null vectors. You take a Hermite normal form of those, and I'm wondering why that's preferred, say, to lattice reducing or something that might make.
Because we liked it when things were triangular, because we had to backsolve sometimes.
Okay, so it's not the size.
So we thought about that, because lattice reduction. We wondered whether lattice reduction would give us sort of smaller exponents.
Yeah, that's what I was wondering.
Yeah, so we wondered about that, but then we couldn't sort of reverse it so easily. So that was the problem. And we like the triangular reversing, because we're doing a Hermite reduction on sort of one part, and we're reducing the size of everything else too. But then we actually sort of have to sort of go backwards. And it's more important in the case of finite groups, it becomes more important because in finite groups, what happens is you end up getting, you start off with fractional invariance, and your variants end up always being polynomial because the exponents come from the Hermite normal form of Vn, which in this case is a square matrix. And so then you have to also work backwards there when you're solving the variables. And so that becomes quite critical. John?
Can you elaborate on the third point?
Okay,
How do you...
I can point you to the paper. No, actually, so what happens is it's like you take your exponents of your numerator and denominator, and you know they must be in the kernel. You don't know the kernel of what. And so what happens is you then take the exponents and you build a big matrix, and now you've got a matrix which is the kernel of something else. And so you do a Hermite normal form of this matrix to find its kernel. That's how it works.
Your scaling symmetries are always monomials, right?
Pardon me?
Your scaling symmetries are always monomials.
Yeah, everything is it's binomial. That's quite important.
Yeah, and you can sort of see it from the dimensional analysis too. If you take the dimensionless parameter and square it, it's still dimensional.
That's right. Yeah, but I mean, yeah. So there's no way. I mean, group actions that
it's
sort
a
of.
little bit of a trick to figure out what's a nice basis for your scaling.
Yeah.
For your invariants, I'm sure that you run through your algorithm to get a good basis.
Yeah. Additives not so good.
You said you have tried it on all the examples in this biology programs, but
Okay, so it's academic examples, I understand. But,
no, but I mean, like, it was sort of like, or is there any publication now happening in biology where those things are applied? Because this can be very useful for them too, right?
but I think this is what Francois has interacted with people in mathematical biology.
Okay.
So that's where that was a motivation where what Francois did. One of the issues with Francois is he would sometimes take his parameter reduction, but sometimes he would require some parameters to be positive. And so you can correct me if I'm wrong. But our thing, sort of, it doesn't matter. We don't sort of have situations where our parameter is replaced by, k is replaced by, p squared or something like that. So which means that k would have to be positive for it to be legitimate. And so, but no, Francois has interacted with people in at Lille and that. So part of our motivation was to sort of what we saw what he was doing.
Actually, in biology, usually everything is positive.
So our advantage is not really advantage.
Concentration, negative concentration does not exist.
So that makes perfect sense.
I actually once talked to another researcher in the field of coding theory, and he had also some application in biology, and some people have made like a huge theory in biology about certain communication between animals and something until they realized how we could put it in the setup and then make our lives easier. So that's why interaction is important.
Okay, I'm going to go sit down because I think Irina is
sure.
going to have her time. Okay?
Well, thank you very much.